Hello! Today's lecture in your course of Fundamentals and Biomedical Application of Quantum Science and Engineering will be to describe to you a very interesting situation. We normally call this a quantum solid model or a model for a solid. Because what is going to do? What is a solid? Is a regular array of potentials, right? If you have the ions, they look like attractive potentials for the electron and so on. But you know, I did a model of atom using a delta function. I did a model of molecule using two delta functions. Now I'm going to use a solid as a sequence of delta functions. So we're going to consider a periodic potential where a particle can move. And there is a message to be learning this, which is the presence of of a concept that we call energy bands. And that's a consequence of quantum mechanics in those solids. The periodic potential can be either repulsive or attractive. It doesn't matter, we just considering delta functions spaced by A. So the distance between two of those things is A. Therefore, the potential, we must write the potential as a sum of delta potentials located in positions that are given by any A. So we have this sequence. N minus 1 A, N plus 1 A, N plus 2 A, N plus 3 A, and so on. And in this case, we're going to put a particle here with some energy. And we want to know what energy is possible to propagate here, right? What energy can we have in here in this situation? That the particle can exist in this potential, everywhere in this potential. And this regularity of the potential is what characterizes the solid. It's very common in science, in biomedical applications, to have periodical potentials, right? To have periodical structures that somehow looks like periodical potential, like this. And then we must solve quantically this, because this is like adding potentials to the system. I could do this. I could start with one delta function, 2, 3, 4, and adding up, you're going to see the bundle of levels forming in different situations. But I decided to do it in a different way. I decided to put the whole infinite number of potentials that makes the solid. And one thing that we have in the solid is a regularity on the potential, right? If I come here, or here, or here, or there, because this is infinite, I see the same thing. And because I have a regularity in the potential, I must have a regularity on the probability distribution, or the wave function. That's a consequence, right? So not only the potential has a regularity of spacing A, but also the wave function will have the equivalent regularity. If I have a bump of probability here, I must have a bump here, I must have a bump here. I must have a bump everywhere, because any position like this is equivalent. So the regularity on the potential shows up on the regularity of the wave function. And that is a condition that we must consider in solving this problem. Very well. So that's the potential we have. It's a collection, infinite collection of delta potentials with amplitude V0 here. I'm going to put the way I wrote here. And n is integer, so you go from minus infinite to plus infinite by A steps of A. A is the regularity of the potential. And So here, because the potential is infinite, I cannot say the wave function dies out to zero in the infinite, right? It must be equal to what I have everywhere. And that this is the condition I have to write up, is the condition that's obeyed by the wave function. So because of the regularity of the potential, when I give a step of 1 to the n, so 1, if I have any, and I go to n plus 1 position, I have equivalent position, so equivalently, we must have the distribution of probability of finding the particle falling the same. So the wave function in one side is equal to the wave function on the next one. So all those positions are equivalent, right? Because that's the symmetry of the problem. There is no distinction between being this or that. They are all the sequence of delta function. When we require that this is the case, we require that the probability of finding the function has to be regularly spaced equivalently to the potential. The only way for this to be true is that I have a function that the square is equal to the other function to the square. This is possible when the function only differs in one to the other side by a phase. Because when we do the modulus square, the phase disappears, right? The complex conjugate of this is minus I times the phase phi times psi star. Multiplied by psi, the phase goes away, independently of what I am. So one of the boundary conditions for this regularity of the potential is that the wave function in one position and the wave function in the next position that is displaced by A must differ only by a phase. Right. This is required to have the same distribution of probability. Okay, then we're going to solve the problem. We have potentials. We know the solution for potentials like delta. That's why I chose delta, because we are already familiar with the solution of delta function. And we must be able to match the conditions of those wave functions at the boundary that's represented by x equal to n plus 1a or any a. We chose one. They are all equivalent, as we said before. And we chose one position. And by choosing this position, we're going to match the wave function, because the wave function must be continuous. So in this, we took this position, n plus 1a, is any position we want. We could do in any position like this, n minus 1, a, n plus 1. I chose this one. Why? I mean, I have to choose one, right? Because everything is equivalent. So I choose this boundary condition, and I'm going to make here the matching of the wave function, whatever is the wave function of the particle, and the derivative of the wave function of the particle. Okay? So the wave function must be continuous in that position, x equal to n plus 1a. So in one side we have what we call, let me show what I want to. Here I say that the solution is psi n, and here I say that it's psi n plus 1. Okay? This will be my notation all the time. Psi n. Let me put in blue here. This side, psi n plus 1 in this side. And I'm going to do the matching here. So this is what we're going to do. And when we do that, we must have, the first condition is that they are equal at this position. We know that everywhere they differ by a phase only. That's not the problem for any x. But on the boundary, they must be equal. And if you remember, we already investigated, and I already explained to you what's happened with the delta function type potential with the derivative of the wave function. You know, even though the wave function is continuous, we cannot create probability by having the potential. We can give it kicks, like suddenly kicks of potential, of momentum. Therefore, the derivative of the wave function has a discontinuity. And I remember I stopped and I made a parenthesis and I showed to you why in the delta function position, the wave function, the derivative of the wave function must have a discontinuity. And I proved to you that the derivative one side minus the derivative in the other side is this term, 2m divided by h bar square, times the value of the delta function applied to the potential, is the integral of the V0 delta times the psi n plus 1. Could be n, but they are equal, right? At this point. At that point. Okay, so those two conditions must be fulfilled at the boundary or at the position x equal to n plus 1a, which is one of the location, any location of this potential. N is arbitrary. I can choose whatever I want. Now, another thing I want you to remember is that when we solve the delta function, it's a very interesting problem because the particle is free everywhere, right? The solution, there is no potential anywhere. So, in this case of the no that they can go everywhere, they are free, really free. So, in between those points where the delta function is located, solutions are like complex exponential, right? Which is a combination of sines and cosines of kx. So normally we say that the solution, they must have the form of a e to the ikx plus b e to the minus ikx, right? And who is k? If you recall when I solved the delta function, k squared is equal to 2m divided by h bar squared times the energy. When I have delta attractive potential, we need to put, if we have a negative energy, to have bound state. It has a minus here somewhere, you know, to make sure that things works okay. And then I get a real exponential, not a complex exponential. But for our case, basically, in the potential, anywhere that's different, that x is different from any a of where is the delta function located, I have for each of these space a combination of e to the ikx plus b to the I minus kx, which represent a flux going that way and a flux coming that way. So each position I have to have a sum of those two terms as a solution. Okay, said that, I have to come to my potential space. So this is, I'm representing a part of the potential space, right? We're going to represent a little part of the potential space between x equal to any a, x2 equal to n plus 1a, and x equal to n plus 2a. So we are in between this situation. And I told you the function here is called psi n plus 1. Here is called psi n, right? I told you that. And we are investigating this frontier here. We are matching the wave function here. So how must be the solution in this side? Remember, this is x. This is not the origin of x. But it is like if I subtract any this is like, this will be the origin if I subtract from x any a, right? If I subtract any a, it's like this is the x equal to 0 type of position. If I subtract any plus 1a, you know, it's like this is the 0 of the solution of x. This is the x. So the solution in this side must be a combination of a e to the I k x plus b to the I minus b e to the minus I k x. But x here, for this region, right, I must subtract this. So this is the beginning of the x. If I subtract for this x, whatever I am, is like the origin here. So I will substitute x by x minus any a for this side here, because I want to use the solution that I know that it's like, you know, it is as if this was x equal to 0. Right? When x is bigger than x plus x, when x is bigger than any a, I am in the positive side. When it is smaller, I'm in the negative side. So the solution this side of the frontier is e a n, because I am in the psi n part, times e to the I k x minus n a plus b n e to the minus I k x minus n a. That must be the solution in this side here. Because in between the two delta, I have this free particle going and coming. So on this side is equivalent to the left side, but now the origin must be n plus 1a. So I have to subtract from x n plus 1a. If I do this, it's like this is the origin of x. Here will be positive x, from here will be negative x, and everything continues exactly the same. But I must label the index of the coefficient n plus 1. Why? Because this is the n plus 1 site, it's the n plus 1 location. Right? And the solution then in this side is a n plus 1 times exponential of I k x minus n plus 1a plus b n plus 1 exponential of minus e k x minus n plus 1a. And then I have the two-way functions in both sides. I just need to match here as I wrote the conditions. Right? So I hope you understand that the solution is the same. I just displaced x. It's like taking the origin displaced by a from one to the other. That's why here is n and this is n plus 1. So if I displace the solution by a, they are the same. As I told you before, they must be, because everything else is the same. The potential is this, it's just equal as I displace, so everything must be equal. Now, as I told you, we're gonna look the conditions in x equal to n plus 1a, which is this boundary. And the first thing is function must be continuous. That's very good that the function must be continuous. So psi n equal to psi n plus 1 in this frontier. So an e to the, if you substitute x by n plus 1a, which is this position, it only ends by having ka here, right? Well, n plus 1, only one survives, the other goes away. So on the left side, we have an e to the I k a plus bn e to the minus I k a. And in the other side, because I'm going to substitute x by this whole quantity here, that gives you 0. So I have a n plus 1 plus bn plus 1. So the demand that the wave function is equal in any position of your lattice or of your potential, because we have a series, it's like a lattice of potentials, right? One-dimensional in this case. The relation between in any site will be this, that the number, this is like this. We saw this already, because this is like a phase. Ka is exactly like the phase, right? So an e to the ika plus bn a to the minus ika is equal to n plus 1 plus bn plus 1. That's the relation between the coefficients in any frontier n, which we classify the way that we got the notation corresponding to the frontier x equal to n plus 1a. Right? Now we have to do the same with the derivative. And we already saw that the derivative in that frontier has a discontinuity. And the discontinuity is 2m divided by h bar square v0 times the value of the psi n plus 1, which is the wave function in that precise position. Taking the derivative of this function gives ik times the function minus ik times this function. So it's ik times an times the same thing plus minus ik times bn, right? It's just, this will come out and the rest stays the same because the derivative of exponential is exponential. So when we apply this condition for this side here, when we apply in x equal to n plus 1a, I'm going to have it to the right side ik a index n plus 1 minus ik b index n plus 1. So that's this condition here, right? So this first part is this condition. The second part is this condition. The second part is minus, so you come minus ik an e to the ika, and it's minus times minus give you plus ik bn e to the minus ika. And that must be equal to the value of the function in that site, which is 2m divided by h bar square v0 times the function, which we know is an plus 1 plus bn plus 1. But we cannot forget that they must differ by a phase. That was the periodicity. That was the periodical condition that we demand. So in the place of an plus 1, we put e to the I phi, which is a phase, times an. And in the place of b, we put bn, in the place of bn plus 1, we put bn times the phase. That does give a equation that, of course, two equations, right? That relates two equations in an, a index n, sub-index n, and a b sub-index n, because the n plus 1 is related to the an by the phase, by exponential of I phi. Okay, so we take these two equations that we show here, right? The continuity of the wave function and the continuity of the derivative, or the discontinuity of the derivative. And we impose the condition that comes the periodicity. And to simplify, to not carry those constants away, I'm going to call lambda 2mv0 divided by h bar square. I did that when I solved the delta function before, and I should have done that before, but I want you to have the feeling that things was progressing here the way it is. So substituting in the wave function, we get now a relation. This is the continuity of the wave function. This is equivalent to say that psi n plus 1 is equal to psi n. It turns out, when we put all the conditions, it turns out that A sub B index n and B sub B index n is related by this. Right? And the discontinuity of the derivative gives this equation here. A relation of an and bn, but now, of course, is the derivative will come in the terms and will come the value of the wave function in the point, so that's why lambda appears here and here. And then you have those terms that comes from the derivative. They are in the previous equation. And what I'm going to do now is divide one equation by the other. When I divide one equation by the other, of course, I have this term divided by this term, and an disappear, because an has to disappear at the end of my calculation, because I chose any site, any position to do the matching of the wave function and the derivative of the wave function, as well as bn. B sub index n disappear, because they should not be there, because that should be true for any place that I have chosen to do this. So this side I get this divided by this when I divide the two equations. Imagine that this is not 0, right? Because if it is 0, this is trivial, so supposedly this is not 0. And this term divided by this term here, this side. So now I have a condition that only relates the periodicity of the lattice with the amplitude of the potential. And K is the energy, of course. Remember that K for us, right? If you recall, K for us is K squared equal to ME divided by H bar square. That's the K. So K is the energy here, somehow, right? Now, when we have a relation like this, it's very nice to multiply, divide by things, rearranging terms in a way that I get terms like e to the ika plus or minus e to the minus ika. The same with phi. Phi is the phase here, right? It's an arbitrary phase. I don't know who is this phase. It's here. And you're going to see that it's not really the important thing. So when I rearrange this equation, which is something you can do better than I can, right? Because you're very good in algebra. This condition, which is fundamental condition for this lattice, for this 1D solid model, turns out to be an equation that relates the phase with the energy and the potential. And this is the relation. So that equation is relating the phase, the energy of the system, the periodicity of the potential, and the potential itself. K is the energy. A is the periodicity of the potential. Lambda is somehow related with the amplitude of the potential. And phi is the phase, which I don't know. But I know that cosines of any angle that represents the phase must be within an interval that goes from -1 to +1. That's I know. So I know that the cosines of phi must be bounded to 1. So the modulus of the cosine must be less equal to 1. That's like to say that cosines of phi must be less than 1 and must be bigger than -1. It has to be in this interval. This is what we're saying. Right? So, because of this, means that I cannot have any K or any, basically, I cannot have any K. I must have a special case where this is true. So it's not any energy I can put in my system. My particle in this periodic potential cannot have any energy. It must have an energy that's represented by K, which is consistent of having the cosines within this interval. I'm going to rewrite this equation because the phase here, the only thing that is doing to me is giving a bound limit, superior and inferior, for this relation. So I'm going to rewrite this as this. I'm going to rewrite this, putting that lambda divided by 2k sine of Ka plus cosine of Ka has to be less equal, right? I mean, let's be correct here. Has to be less equal than 1, has to be less bigger or equal than minus 1. That's the condition for the energies. That's the condition for the relation between the periodicity, the energy in K, and the potential. This expression, lambda divided by 2k sine of Ka plus cosines of Ka, is an oscillatory function. So I'm going to represent the function here. So this is just a drawing, of course. I'm not being very careful. So that in this axis, vertical axis, I'm plotting this whole thing here. Of course, this can be bigger than 1, right? I have many examples that will give sinus plus cosinus bigger than 1, even multiplying by this. So that's this function. It goes, comes back, goes, comes back, and in fact it goes as K grows. This goes to attenuating because there is this K here that is killing the sine. So the amplitude is going down as we oscillate, as a function of Ka. Now, we said that this must be bound to plus 1 and minus 1. So this part of the plot here cannot exist. So these energies compatible with this part cannot exist. The only part that can exist are the ones that are bounded between 1 and minus 1. So from here to here, which is this interval of Ka. Or jump this part, this is a gap, comes to this part, between minus 1 and 1. Another gap, plus 1 to minus 1. So you see that I have small places of Ka that's allowed. It's not energy. It's not any energy that's allowed. Only energy that are in these intervals of Ka. Interesting, right? Because the rest of it is not allowed. It's forbidden. Anything that gives values bigger than 1 or smaller than minus 1 is taken out. And because the K square is 2m divided by h bar e, so Ka square is basically 2m h bar square e a square. Or, right, here I kept a and a, but just to be redundant. Because along those intervals, we have an interval of energy possible, right? Now, this is what I want to say, that here energy is allowed, here energy is allowed, here energy is allowed, and so on. So when I make a plot, because the K square is related, this region will give a K square that's related to the energy. This is what we want to say. You don't need to worry about this A square because they're going to cancel. If I represent in a plot of the energy, what I get is there is an interval of energy that's allowed. Particle can have that interval of energy. And then there is a gap. Cannot have energy in this gap, because that is the forbidden region. And then there is possibility of having energy in another region of energy. It's another band. And another band, which is the allowed energy range. So this gives, for the solid, what we call a band structure. And band structure is very interesting because it's the position where the particle can have energy. And if you remember, I consider a sequence of potential and I gave energy. I gave energy to the particle. I gave momentum to the particle. And for the particle to move around and be everywhere here, to be conducting through the lattice, to be moving through the lattice, it needs to have those energies. Otherwise, we will not have. And by the way, this represents everything because I have those barriers. This can be bound states or free states, or states that they localize everywhere, right? Okay, so the energy of the particle actually, is E h bar square divided by 2m k square. Remember, it's like this everywhere. This is the energy that, if you remember, the k we got is the k consistent with the free particle. That is in between the things. And only possible in some ranges of energy that characterizes the bands. So the structure of a solid is not exactly like the structure of an atom. It has bands, interval of energy which is allowed. Okay, well, there are another way of representing this, because this is the energy of the particles. Another way of doing this is, this is a parabolic with k. But you cannot have any k. You can only have k's determined by the for the allowed region. So you have a kind of, maybe I should do that. This will be very illustrated here. So if I call the energy equals to h bar square divided by 2m k square, right? This is what I'm doing there. So that's a parabola, like if I put k here and energy here, this will be like a parabola like this. But we learned that it's all allowed in some regions of, I can only allow here, then there is a gap, and then I'm allowed here. So actually this goes, stops, continues this, stops, continues there, stops. So you get this dispersion relation with gaps, with forbidding energies. Here is forbidden. When I put red here, means cannot have it, right? Just for you to understand that sometimes they put that parabola in the textbooks. So this is a model of a solid, and actually this model is called Kronig-Penney model for the solid. It's a collection of periodical potential and particles. If I have like electrons, we have to learn a little more about the many electrons there, right? They can fill it up, those bands, and then they are arranged there, fill it up. And sometimes we have a band that's called the Valence Band, where the electrons are kind of localized on the potentials. And then there is the conducting band, where the electrons are free to move. But to go from one to the other depends on the type of solids. When I have these two possibilities overlapping, I have a conductor. So almost nothing can make the electrons to be free and move. Whoop. So I have the valence band, which is this allow energy, fill it, and then I have the conducting band overlap with it, basically, close by, near, in fact, touching. So they can go to be free and conduct almost costing nothing, no energy at all, any small energy. If the gap is a little bigger, it will cost a little bit. So the two bands are near, but not exactly overlapping. This is the semiconductors. So for them to conduct, you must give a final energy, which is the threshold for the system to start to conduct, to produce particles that will free. And when it's very far, sometimes happens that you have a very far apart conducting band from the valence band. I have an isolator. Does not conduct, except that if you break down this, if you put a lot of field, a lot of energy, and those bands, they depend a lot of external fields, so I can manipulate those bands and everything. And believe me, this solution for the solid is basically one of the bases of solid state physics and one of the bases for electronics, because by putting field I can manipulate those bands, make it things to conduct in some field or not, and do all kinds of interesting games that giving origin to manipulation of current the way we want and have those wonderful devices we have. Okay, so today we learn the solid, a model of solid, and we see the origin of the bands, the structure of the bands, the energy bands, which is, of course, when we do the solid state physics, it is a little more complicated depending on the symmetry of the lattice and everything. But in 1D, it only gives the origin of the bands. So you see that electron is allowed to have energy within an interval of momentum or energy, and this giving the bands of the solid. Okay, well, next lecture we should go on, and now we're gonna jump to the molecules and atoms. See you there, bye-bye.